Hello everyone and welcome to this project presentation. Today I am very pleased to present a comprehensive project that seamlessly integrates numerical simulation with advanced visualizations. This project is part of my numerical technique laboratory and I am Apurva Pramanik Turjo and my friend Mohammad Nafiz is there. We have both worked on this project. The name of our project is 3D visualization of rocket launch trajectory in Unity using flight data from MATLAB. In this project, we have aimed to transfer raw discrete data typically found from a spreadsheet into a continuous and physically accurate flight path. Our core objective was to render this calculated trajectory as a dynamic 3D animation within the Unity game engine. This project has basically two sections. The first section is the numerical solution and data processing in MATLAB, and the second part is the 3D visualization in Unity. So in the MATLAB section, we will first import some data and we will import this data from an Excel file. The name of that file is thrust-mass-flow.xlsx. In this file, we will obtain the thrust, mass, and mass flow rate at different time of flight of the rocket. And one thing that is, we have considered Space Shuttle as our rocket. It is a two-stage rocket with two solid rocket boosters and three Space Shuttle main engines. There are some realistic events in our simulations, that is the engine throttling events, stage separation event, second stage separation event, and also very important, the gravitational maneuver. To get the complete trajectory of a rocket, we need to solve some equations that are related to the flight dynamics of rocket. And those equations are this velocity equation, and downrange distance equation, flight path angle equation, and altitude equation. After solving all of this, we'll get the velocity, downrange distance, altitude, path angle at continuous time. And from this data, we can simulate our data in Unity and get a very clear visuals of this simulation. Uh, we'll we can look into this velocity equation in which velocity depends on the thrust, drag, and mass. Drag is a very nonlinear force in case of rocket launching because the drag force basically depends on the rho parameter. Rho means the atmosphere air density, and air density is changing with respect to pressure and temperature, and the pressure and temperature is also changing in a three different ways with respect to altitude. If the height is greater than 25,000 meter, the temperature and pressure will change in a different way rather than the 11 to 25,000 meter. So the since the pressure and temperature is changing non-linearly, the rho is also changing in a non-linear manner. So does the drag force. That's why it is very tough to simulate the launch trajectory or overall trajectory of a rocket. So in the next part, we have built a GUI, graphical user interface. Okay, we can open the GUI right now. This is our GUI. There is couple of plots here: altitude versus downrange distance, velocity versus time, thrust versus time, path angle versus time, and from our discrete data files or discrete input files, we will build some continuous curve here from that file, and we have a MATLAB code that helps us to generate this curve. The MATLAB code is here. This is our MATLAB code. This is the function. This function is invoked by the user through GUI, and there are some input parameters here. So we have some arrays, and we will store the flight data in those arrays. To get data, we first of all we need to um, interpolate our discrete data that was obtained from the thrust mass flow data file. There is the thrust interpolation, and there is mass interpolation also. To demonstrate the engine throttling very properly, we have to manipulate this interpolation manually, and we have inputted some data into the mass and thrust um, factor from 90 to 120 seconds and 30 to 40 seconds to demonstrate the engine throttling properly. So the rest of the course also deals with solving ODs. We have used Euler method to solve ODs, and those ODs are nothing but those velocity, downrange, and path angle equation that was written here. Those these ODs are solved in the MATLAB using the Euler rule. So after solving these ODs, we have obtained some um, column vector here, like x export, y export, gamma export, velocity export. All of these are related to the flight dynamics of the rocket. So from these matrices, we'll combine those column vector array. Sorry, we'll combine those array to create a output file or export file that is trajectory data. We will compile those column vector into this trajectory data.csv. This trajectory data.csv will help us to link up with the Unity. So once we execute our GUI, the file will be created. So this is our GUI. We have to select our input file. After selecting the input file, we have to press this execute button. After pressing the execute button, the function is invoked in the MATLAB code and the plots are generating here. Altitude is increasing very fast in the initial time. Velocity is changing gradually. Mass is also changing in a very uh, gradually and linear way. Path angle is also changing. After the gravity turn was initiated, the path angle was decreasing from the 90 degree. Initially, it was in a vertical position, and we'll say that when the simulations end, the rocket will be in a horizontal position. So the path angle is changing and path angle is decreasing. That's why the rocket is in a horizontal uh, situation here. The rocket is in the horizontal position here. That's why after some time we'll see that the altitude is not changing that much of rapidness in comparison to the initial time. The altitude is almost fixed after the horizontal distance was crossed over 1000 kilometers. Since we have Space Shuttle as our rocket, it is a two-stage rocket. So there are two thrust levels here. The first stage has a very high thrust compared to its second stage. Since the second stage only consists of three Space Shuttle main engine, and the first stage has two very big solid rockets boosters, and that provides the mm, bigger portion of thrust in the first stage. Since the thrust level is very high on the first stage, the mass is also increasing in a very the mass is also decreasing very rapidly into the first stage. We see that the rate of decreasing mass in the second stage is very much less than the first stage. The velocity is also increasing in the second stage very much less than the first stage. The slope on the first stage is higher than the slope on the second stage. The slope of first stage is very much higher than the second stage slope. So that means in the second stage we are getting less thrust. The altitude is changing in a less rapidly, and path angle is switching to 0 degree. So this is the continuous data we have obtained from the discrete data file, and this file is compiled. This plot is compiled as a matrix in trajectory data.csv file. So here is our trajectory data.csv file. This data will help us to visualize our simulation in 3D. So now we can proceed to Unity. This is Unity. We have this Unity game engine. so that we can simulate our data. There is our application STS launch, and STS launch data. If we open the STS launch data folder, there is no trajectory data.csv. Since there is no trajectory data.csv, we won't see anything moving in our simulation. Here we have opened our applications. If we press the play button, we will see that nothing will happen. Look, the speed is 0, altitude is 0, launch time is 0. We are in the lift off position here and nothing is moving. This is because we haven't exported our trajectory data.csv into the specific folder of the applications. So we have to quit it right now. We need our trajectory data.csv that was generated moment ago by the user using the GUI that is here. We need to copy it and we need to paste this file in STS launch data folder. So we have pasted here. So let's now reopen our application. There is our application. There is our overall scenario of a simulations. There is a space shuttle. There is a launch pad also. There is a chase camera option here. We're in a lift off situation. This is the speed slider. By using this, we can control the simulation speed. If we press the play button, we will see that the rocket engine is firing and the rocket is moving upwards. We will see that the speed is increasing and the altitude is also increasing. When the rocket is out of our main camera view, we will switch to the chase camera. This chase camera will help us to follow the rocket until the simulation ends. We will see that the 3 solid rocket boosters is firing along with the space shuttle main engines. After 30 seconds, we will see that the rocket is tilting. This is due to the gravitational maneuver and the path angle is changing from 90 degree to gradually it is changing to 0 degree. We will see that the rocket will be in a horizontal position when the simulation ends. The altitude is almost 8 kilometers and the speed has crossed 1000 km per hour. The rocket will burn for almost 510 seconds and the solid rocket boosters will be separated after 120 seconds. So that the first stage burn will complete it within the 120 seconds. When it's right now 110 seconds, after 10 seconds it will be switched off. So we have 1.5 minutes passed from our launch. We may increase the speed a little bit. We will do that after the first separation. This altitude is almost 30 kilometers. Altitude is changing very fast and the speed is also changing in a fast way. Fast separation in 3, 2, 1. The first separation was done. Speed is almost 6,500, 600 and 6,500 km per hour and altitude is almost 50 km. We will see that the speed is now increasing more fast than the previous time and the altitude is also changing. So we may increase our simulation time here. Here we have fastened our simulations and we are seeing that the rocket is almost in a horizontal situation. Still there is some angle between 2 to 5 degrees and that angle will be converted into 0 after some time. Almost 4 minutes has passed. The speed is now 10,000 kilometers. Altitude is 90 kilometers. Surface separation is completed and the rocket is currently in the second stage and 3 space shuttle main engines burning only. There is an external fuel tank. From this fuel tank, the rocket is drawing fuels, taking fuels from the external tank. This rocket main engine will burn out at 510 seconds. That means 8 minutes and 30 seconds. Then the speed will be fixed and the altitude will be fixed also. We're seeing that the altitude is right now 96.8 kilometer and speed is 27,000 kilometer. Second stage burnout done, main engine cut off. This is main engine is switched off. There is external fuel tank that will be jettisoned and that has been jettisoned right now. And the speed is not changing as all engines are shut off and the altitude is 97.4 kilometers. So the rocket is entered into the orbital insertion mode and our simulations ends here. So that was our overall simulations, and we have seen that the rocket was moving very realistically, as we have seen the launches in ground. So this is our overall project, and we have tried to make it more realistic. And since we have shown the gravity turn, engine throttling, and so many things, we think that we have executed our project or completed our project successfully. And this was very interesting. We have learned so many things from this project. And I hope that the knowledge we have gained from this project will help us to explore the other things of rocket launching very convenient way. So thank you very much to be with me. Thank you.